Hey everybody, the purpose of this video is to understand the conceptual connections between Gibbs free energy, spontaneity, and equilibrium. These connections often lie in interpreting mathematical expressions to understand what they mean. To review a few important concepts, Gibbs free energy is delta G, and it is equal to delta H minus T delta S. And that means that delta G equals minus T delta S of the universe, or that delta G is directly proportional to delta S of the universe, which means that we can use it to predict spontaneity. Specifically, as you may recall, for a reaction to be spontaneous, delta S of the universe has to increase, which means that delta G for that process must be less than 0. And then the forward reaction is spontaneous. If delta S is less than 0 and delta G is greater than 0, then the process is non-spontaneous, and instead the reverse reaction would be spontaneous. If delta G is equal to 0, then it is true that the system is at equilibrium. When we look further and think further about this delta G equals delta H minus T delta S equation, we realize that Gibbs free energy is very temperature dependent, and that ultimately we have 4 different scenarios that might play out with this equation. The first scenario is that delta H may be negative and delta S may be positive. If this is the case, then delta G will always be negative. In other words, at all temperatures, that particular process is spontaneous. The second scenario, if delta H is positive and delta S is negative, then delta G will always, regardless of temperature, be positive, and therefore that process is always non-spontaneous. The 2 very temperature-dependent processes are the final 2, and they occur when delta H is negative and delta S is negative, and that process is spontaneous only at low temperatures. At high temperatures, it will be non-spontaneous. The final scenario is when delta H is positive and delta S is also positive. And this process gives you a spontaneous or negative delta G at high temperatures. So these processes with positive delta H and positive delta S are spontaneous at high temperatures with a negative delta G resulting. It's important to understand and be able to recall these 4 scenarios as you work with Gibbs free energy problems. Now let's turn our attention to delta G and equilibrium. In general, it is true that under non-standard conditions, delta G equals delta G0, or the value of Gibbs free energy at standard conditions, plus RT natural log of Q, where R is the universal gas constant, T is the temperature in Kelvin, and Q is the reaction quotient. If we are at equilibrium, Q equals K, and therefore delta G of reaction, or delta G, equals 0, and therefore we end up with delta G0 of reaction equaling minus RT natural log of K. If you study this equation carefully, 3 scenarios will present themselves. If K is less than 1, then delta G0 of the reaction will be greater than 0. This means that the reverse reaction is the spontaneous process, or, if you prefer, the forward reaction is non-spontaneous. The second scenario is delta G0 less than 0, in other words, a spontaneous forward process, and this only occurs if K is greater than 1. In other words, the forward reaction is spontaneous or product favored. The final scenario occurs when delta G0 equals 0, and this only happens when K equals 1, which means the reaction is at equilibrium and we have relatively equal amounts of reactants and products. At standard conditions, it is possible to predict using delta G0 the spontaneity of a process. Deviating from standard conditions, however, we will need to return to our original equation, delta G equals delta G0 plus natural log of Q. Let's synthesize these ideas in a couple of problems. Here is our first problem. We have two tables of statements here for two different chemical equilibria. And what we want to decide is if these statements all agree or if one of these statements might be false. So the maximum here in either scenario is that one statement is false or that no statements are false. Those are the two options. And if one of the statements is false, we want to indicate which one is false. When I think about these problems, and we'll start with the table on the left, when I think about these problems, I always start with the value of K. It's just easier in my brain. So on the left here, we've got a value of K less than 1. Well, if K is less than 1, in other words, between 0 and 1, the natural log of any number between 0 and 1 is negative. Okay? The natural log of any number between 0 and 1 is negative. That means that these first two statements definitely agree. So we'll just put stars next to them for right now. Those two definitely agree. And if the natural log of K is negative, remember that delta G0 equals minus RT natural log of K. So if the natural log of K is negative, we've got a negative times a negative, which would equal a positive, which means if K is less than 1, and if the natural log of K is less than 0, both of which agree, then delta G0 must also be greater than 0. So the last statement agrees with the first two. The only statement remaining in question is the third one, and it says delta S0 is greater than delta H0 over T. And this statement, it turns out, is false, and here's why. If delta G is greater than 0, and we've already determined that that is an agreeable statement, then it equals delta H0 minus T delta S0. And if you solve this, that means that delta S0 is less than delta H0 divided by T. So the third statement here is false. The third statement here is false. Let's look at the second example. And again, I'm going to start down here at the bottom, and I'm going to make an assumption that K equals 1 is a true statement. Well, if K equals 1 is a true statement, the natural log of 1 is 0. So then the natural log of K would equal 0. So the first and the last statement agree here. The first and the last statement agree here. And if this is true, looking at our equation again, delta G0 equals minus RT natural log of K. If the natural log of K is 0, then delta G0 would have to equal 0, which means that the second statement here saying delta G0 equals 1 is absolutely false. If you want to prove that the third statement, delta S equals delta H over T, is true, you can do that in a similar fashion to what we did on the first example, but trust me, folks, it's a true statement. Let's look at one more example to synthesize these concepts together. And that is this problem. We have the reaction here of nitrosol chloride decomposing to 2 moles of nitrogen monoxide and 1 mole of chlorine gas. And we are told here that delta G0 for this reaction is 41 kilojoules. Suppose a reaction vessel is filled with 6.79 atmospheres of nitrosol chloride and 1.41 atmospheres of nitrogen monoxide at 1122 Celsius. Answer the following questions about the system. The first thing to note here, they give us delta G0 for this reaction, but it doesn't tell us anything because we are not at standard conditions. We have pressures much greater than 1, and we do not have a temperature of 25 Celsius. So we can't use that delta G0 for anything right this moment. We're going to have to rely on our values and our understanding of equilibrium for a moment. And so it is good to note the initial amounts of each reactant and product. So we have 6.79 atmospheres of nitrosol chloride, and we have 1.41 atmospheres of nitrogen monoxide, which means initially, I'll just put an I here for initial, we don't have any chlorine. The first question says, under these conditions, will the pressure of nitrosol chloride tend to rise or fall? Think back to our understanding of equilibrium. If this reaction starts, it must proceed to the right because there is initially no chlorine, which means the concentration or pressure of nitrosol chloride in this scenario is going to fall. It is going to decrease. Second question, is it possible to reverse the tendency by adding chlorine? In other words, if you said that the pressure of nitrosol chloride will tend to rise, then can it be changed to a tendency to fall by adding chlorine or vice versa? Well, we said it was going to fall, so the question is, if we add chlorine to this mixture, will we or can we reverse this process? This is a Le Chatelier's principle question, and the answer here is absolutely yes. Because if we add enough chlorine, we will actually push this reaction back to the left, which will increase the amount of NOCl in the mixture. So the answer is absolutely yes based on Le Chatelier's principle. Last question. If you said the tendency can be reversed in the second question, which we did, calculate the minimum pressure of Cl2 needed to reverse it. Round your answer to 2 significant figures. We have to do this calculation, and we're going to need some more room. So let me go to this blank side and rewrite our reaction. 2NOCl, which was 6.79 ATM, reacts to produce 2NO, 1.41 ATM was our initial amount, plus chlorine, which we initially had 0. For this reaction, they told us delta G0 is 41 kilojoules, and that the temperature was 1122 Celsius, or 1395 Kelvin. Okay? We want to know the minimum amount to reverse this reaction, so we want to know where delta G goes from negative to positive. Well, that, of course, happens when delta G equals 0. And you recall delta G equals delta G0, which in this case is 41 kilojoules. I'm going to change it to joules and go 41,000 joules, plus R, which is the gas constant, 8.314, times T in Kelvin, which is 1395, times the natural log of Q, which is the reaction quotient. We want to find out what Q has to be for this to be at equilibrium. In other words, for delta G0 to equal 0. If we can find the value of Q, then we can solve for the minimum amount of chlorine gas we need. So if you rearrange this equation, you end up with the natural log of Q equals negative 3.54. Using the opposite of the natural log, the natural exponential function, we get Q equals e to the negative 3.4 power, or Q equals 0.0290, which is going to be equal to, based on our given reaction above, the pressure of the products over the pressure of the reactants, 1.41 squared, don't forget the squared, times the concentration of Cl2, that's what we're looking for, or the pressure of Cl2, divided by the concentrations of the reactants, 6.79, careful there, squared. If you rearrange this and solve for Cl2, you will get that the pressure of Cl2 must be equal to 0.67 atmospheres. So if we put at least 0.67 atmospheres of chlorine in this system, we will reverse this process, and instead of the concentration or the pressure of NaCl falling in this system, it will actually rise. I hope this video gives you a little bit of insight into the relationships between Gibbs free energy, delta H, delta S, and spontaneity.